introduction and the opportunity to speak in this context. So this talk will be a little bit of a throwback to the old era of mirror symmetry. I guess in this subject, anything over 15, 20 years is considered classical. So one might call that this is about the more classical aspect of mirror symmetry. So this will be, roughly speaking, a study of the interplay between three objects. Mirror symmetry, of course, is the central object. And the main point here is about using mirror symmetry to say something about special functions, including generalized hypergeometric functions and complex geometry. And sometimes statements about the lower two items tell you something about mirror symmetry as well. All right. So basically, what we like to do is to use periods of Lian manifolds from the D model to prove statements about special functions and the associated D modules. So to also say something about certain homological descriptions of D modules. And in the end, we would also like to use periods of Lian manifold to say something about certain general type and final problems. Okay, this is based on a long series of joint works with starting with Spencer Bloch, Lei Fu, and An Huang, Srinivas, Yao, and Qingwen Zhu. Okay, so this is roughly my lecture plans. Probably don't have time to go through every one of them in detail. So I will start with a what we call the Riemann-Hilbert problem for periods. And one step toward the solution to that problem is to give an explicit, in fact, two explicit descriptions of periods and the D module for periods and residues. And and the next three items is about applying what we learned from these descriptions to solve certain old problem in mirror symmetry. So first of which is the solutions to GKZ system. Basically, we are giving a new geometrical interpretation to solutions to GKZ system, a certain GKZ system. And again, HO problem in mirror symmetry, the large complex structure limit problem. Finding the appropriate point in the moduli space of Lian manifold to expand the count curves. And the next item is about using these D module descriptions to say something about special functions, using the connection between special, known connections between special functions and periods. And finally, we would like to say something about periods of general types and final toric hypersurfaces. And if time permitting, I might even get into some open questions. Okay, so let's start with the a very familiar setup. So you look at a family of compact complex manifold. I'll call them pi throughout the lecture, and the total space will be called script y. The fiber will be called YB at each base point B. So then you have the familiar Gauss-Manin construction. So you look at this flat bundle associated to the family. For each K, you have such a flat bundle whose fiber is nothing but the K cohomology group of the fiber of the family. And you can look at the dual bundle, and you have the standard Poincare pairing between the two. And the local parallel sections are just the representable by homology classes. a space of global section of this flat bundle E. I call it this space capital lambda. So for each lambda, we want to integrate. Well, for each lambda, if you evaluate lambda at a point, it's just a k-cohomology class. Think of it as a round class on the fiber of the family, and I want to integrate it. Okay, so when you do so, you get an analytic function, or germ of analytic function we call period integral. Okay? So this period integral depends on the choice of a parallel section of your Gauss-Mani connection, so namely a k-cycle. Now, I won't have anything to say about these things in this talk, except for the case when you're in the middle degree. So throughout my talk, K will be the degree of the cohomology group, will be the dimension of the manifold. And I'll drop the reference to D and just call the sheaf generated by, or the local system generated by these analytic functions, capital Pi. So I refer to this as the period sheaf. Okay, now next I want to specialize it, set up somewhat. Instead of a general family, I want to look at a family of hypersurfaces in a fixed ambient projective manifold, n-dimensional ambient projective manifold. So my D now becomes n minus 1. Okay, so this is a family of hypersurfaces parameterized by a set of sections of a line bundle. So in this setup, there's one more gadget you can play with. Namely, instead of just looking at the previous flat bundle, you can look at this local system generated by the complement cohomology, the middle complement cohomology. So this is the complement of each fiber. You take the n cohomology. They form a local system, and I'll call these, refer to this local system as with a prime, E prime, and number prime is a flat connection on this side. Okay, so now I want to pick a space of sections in the following way of this bundle E prime. So notice that just by counting degree of line bundle, you see that for every section in this line bundle, this line bundle L twisted by a canonical of X, you can define a global sections of my flat bundle E prime as follows. So at each point, this is nothing but given by this formula. So this is thought of as a degree n form, meromorphic n form with pole along the zero locus of P. Okay. Here, the capital omega is a certain canonical holomorphic n form on certain principal H bundle over X. The detailed construction of this omega is a long story, but it's not very difficult. And the details is first written in the paper of Yao in 2012, and in a special case, and in full generality in a preprint with my student Chen. Okay, so given this section lambda G, I want to look at all of these guys and put them together. So this would be what I call lambda prime. So lambda prime is now a certain space of global sections of this flat bundle whose generic fiber is this complement cohomology and HN. Okay, so now I do the same thing as I would with period integral. Instead of considering the periods of the family, I consider now taking this meromorphic form and integrate over the cycle. So these cycles are just homology class in the complement of my family Y. So again, you get a function germ at point B. I refer to these as residue integral, mimicking having in mind the complex one variable case. This is literally classical, good old classical residue, Cauchy residue. So this is sort of the higher dimensional analog. Okay, so the period sheaf and the periods on the residues are related in a very simple way. Namely, if you take for each of these this meromorphic form, if you take the Poincare residue, what you get is a form, a holomorphic form of the hypersurface YB. So therefore, you can pass between the two spaces. From this space of meromorphic form, you get a space of holomorphic forms on the fiber via these Poincare residue. So in effect, what you get is that this Poincare residue allows you to get a canonical embedding from the period sheaf to the residue sheaf. There's this formula, this identification. So how do you do that? Well, for each gamma for each gamma you have this thing is a period, and for each such cycle you can construct a sort of tube over the cycle, and that tube over the cycle becomes a cycle in the complement, and you integrate over this meromorphic form, and then you easily show that you recover the original period. Okay, so in this setup, I now am looking at two separate local systems. One sitting inside of the other. The two are, in general, different. The second one is usually bigger, much bigger. Okay.
So
all right.
Which one is the bigger one relative?
Yeah, the one for the complement. Yeah, the residue is a bigger one. Okay, so here's a sort of a problem that literally goes back to Riemann, although not in this such a general context, which is that you get these two sheaf of analytic functions, local system of analytic functions. So what you want is you want to construct a complete differential system of equation, a system of linear PDE for each of these sheaf of analytic functions. Complete here is a keyword. So complete here means that you want the system in such a way that its solution is precisely the sheaf that you started with, no more, no less. Yeah? Okay. So why do we care about such a problem? Well, it turns out that having a good description of the differential system gives you many interesting applications, including the symmetry. The point is that the differential system essentially captures all the information about these period sheaf. So instead of dealing with these sort of local object like periods and residues, you have a global object to work with, the differential system. Okay? And then because differential systems are intimately connected to D-module theory, you have the whole host of tools at your disposal to analyze these objects. Okay, now, so this is a nicely stated problem. Unfortunately, except for very few cases, and most of them came from physics, the problem were largely unsolved until quite recently. Most of the solved cases are sort of rather very simple in nature, like one variable, or cases with very obvious symmetry. Okay, and these known cases are almost all of them were motivated by mere symmetry. Okay, so for example, one important case, the case of a quintic threefold, were not known. I mean, the answer to this problem were not known until 2 years ago. 20 years ago there was a conjectural answer, but the conjecture was not settled until very recently. I'll get into that in a moment. Okay, so let me start with some very elementary examples that are also very classical. So let's start with this toy example. Probably this one is so simple that even the classical people avoided it. Okay. Okay, so you look at my ambient space is now P1, and we'll pick this line bundle, so O2, and so the hypersurface defined by this line bundle is just defined by quadratic polynomial. So I'm going to think of the coefficients of my polynomial, these a's, as coordinates on the space of polynomial. So these coordinates will play the role of parameter space. Okay? All right. So if I take a point in this set, so C3 refer to the space coordinatized by A0, A1, and A2. So I take out this so-called discriminant locus. So this quadrant is exactly defining when the 2 points defined by the polynomial collide, right? That's the discriminant. Okay. So the Calabi-Yau in this case is just a pair of points. The smooth Calabi-Yau is just a pair of points. Okay. Now, so you have this family, and I noticed a typo here. So you take the symmetric product of C3, not SL2. I mean, you could think of it as SL2, but C3 is C2, not SL2. C2. So SL2 acts on C2 in a canonical way, so it acts on symmetric power of 2. And I think of this A0 as the basis of this vector space. Okay? And you can, of course, it's elementary to write down the operator that represent the SL2 Lie algebra on this linear representation. So I'm going to write like that, where the xi ij is the matrix representing the element xi in the basis AI. Okay. Okay. So now you have 3 operators, and it's quite elementary to check that, basically by hand, that the solution to the Riemann-Hilbert problem for both of these period sheaf and residue sheaf are given by this differential system. So this system has sort of three sets of operators. One comes from this nice quadratic operator. Notice that it's a binomial. And the next type of operator is the Euler operator. So that refers to the fact that your residue is homogeneous of degree -1 in the variable A. Okay, so this captures it. So these are sort of the obvious thing you can write down. And finally, there is the symmetry operator. Because the setup is completely SL2 equivariant or PSL2 equivariant. So you expect that these are all these must be some of the operators that behave very well when you hit it on the period sheet. And indeed, they are. Okay, so the question is, you write down this obvious operator. How do you know that this is complete? Well, you do it in your next slide. You solve the system. Upon solving the system, you see that the system has exactly one-dimensional solution. And it's given by this nice formula. It's exactly the discriminant locus to a power minus 1/2. The power is to make sure that this thing comes up to have homogeneous degree -1. Okay. Okay, so this is your solution sheaf. And because it's one-dimensional, you have no place to hide. The two must be the same. Okay? And so you will found your system that reproduce the period sheaf and the residue sheaf. Okay, let me make a few comments. If you take this differential system and replace SL2 by a smaller Lie subalgebra, namely you replace SL2 by its Cartan, which is in this case just a copy of the complex number, the one-dimensional abelian Lie algebra. Then you recover the sort of the simplest example of a GKZ system. Okay, so now let me, from the baby example, let's go up to an adolescent example. Let's look at Lian. So in this case, I want to look at the analog of that will be this universal family of CY hypersurfaces in CPN. And again, it's defined by degree n polynomial, and this is my notation. Okay. Okay. So these mu I are the exponent whose this exponent that adds up to n plus 1. Okay. Now in this case, there's a well-known classical formula that gives you a section of this flat bundle. Namely, you take this omega form. So this form is really not defined on Pn, but it's defined on the C cross principal bundle over Pn. Right? These are homogeneous coordinates. Okay? But you can think of that as a form on the C cross principal bundle. But so when you divide it this way, you see that this ratio makes sense as a form on Pn. So this will be a canonical section, and so my lambda prime in this case is one-dimensional. Okay, so it turns out that the SL2 example generalized fairly straightforwardly to this case, and so instead of SL2, you got SLn plus 1, acting on this symmetric power. So again, this is thought of as the space of all degree n plus 1 polynomials. And I choose the basis to be these the coefficients of the coordinate coefficient of my defining polynomial, this A. Okay. And again, the action is given by this sort of first order differential operator. Okay, so this is an old observation that goes back in 95. So this immediately generalized the SL2 case, namely, well, partially generalized the SL2 case, to say that the period sheaf and the residue sheaf are solutions to this differential system. So again, these are the obvious operators you can write down. The symmetry and the Euler, keeping track of the homogeneous degree. And these are the ones that sort of, if you apply this operator on the section I wrote down, omega over f, you see immediately that this operator has to kill that form. And therefore, it has to kill the residue and the corresponding periods. So these are some of the obvious things you can write down. So then the obvious question is that all? Is that all that you need to pin down the period and residues? Well, it turns out that this question took 20 years to settle. Before that, let me go back a couple of years. So it turns out that if you consider a slightly different problem, namely sort of in affine geometry rather than in projective geometry, you look at the family of affine toric hypersurfaces. So you take this Calabi hypersurface surfaces and you intersect it with the dense torus inside your CPN. So these are all a family of affine hypersurfaces. So you can still talk about residue and period in a completely formal way. And it turns out that these periods and residue satisfy the so-called GKZ system, where you replace the SL2 by its katan. And this was discovered by Batirev in '93. Basically, his paper was the one that made the connection between near symmetry and GKZ system. Via these toric hypersurfaces, these affine hypersurfaces. So later on, there are many papers that follow it that soup it up to the projective case. However, if you look at this GKZ system where SL2 is replaced by n plus 1 is replaced by its katan, the system turns out to be never to be complete. They are neither for the period sheaf nor the residue sheaf. Meaning the GKZ system has too few operators. Okay, so coming back to this completeness question. Now, one thing I want to draw your attention to is these binomial operators. So on the one hand, it's GKZ type because it's binomial and homogeneous. But the more important observation is you notice that these relations are very similar to what you would have if you try to embed a projective space into a higher dimensional projective space via the Segre embedding or the Veronese embedding. So these are sort of the Veronese relation, namely the sub-variety inside the higher dimensional projective variety is defined exactly by this sort of relation. Of course, this has nothing to do with differential operator. They're given by polynomial relation, and they are exactly of this type. And that turns out to be the key link to generalize this problem and solve this completeness problem. Okay. So this completeness problem was settled recently in a joint work with Spencer Block, Huang, Srinivas, and Yang. So the statement is that tau I wrote down above is complete. Okay, so much of my talk will be to sort of lay out a general context for this result, which is that this is actually a very special case of a general result of arbitrary projective G variety. Okay, so this is sort of the second part of my talk. So I want to introduce a class of differential system or D module, which I will call tautological system. So here's the initial setup. There's quite a bit of notation, but I'll sort of give you a baby example that is easy to keep track of all this data, to help you keep track of all this data. So the initial data is that you have three pieces of stuff. So G is a complex algebraic group. Use German G for its Lie algebra. X is a given projective G manifold. And L will be a G equivariant very ample line bundle. The very ample condition is not essential, but to make the discussion sort of smooth and not avoiding many digression into technicality, I will stick with this simple condition. So L is very ample line bundle. All right, so from the initial data, you can make up these the following thing. You look at the space of sections and look at the linear dual called the space V. So V will play a very essential role throughout. Look at the space of polynomial functions, which I call CV. And because I have an equivariant line bundle, this V become a rational representation of the group G. And that Z denotes the corresponding Lie algebra action. Since I won't be talking anything about the central of the Lie algebra, so Z should not cause any confusion. So Z is really an action, not the center. Okay. Now, because I started from a very ample line bundle, I get for free what's usually called a tautological embedding, namely the embedding corresponding to the very ample line bundle into the dual of the section space, PV. Okay. So I call this embedding map phi. Okay. So from my data, I now get sort of this derived data. First, a defining ideal for my the image of the embedding X. So call the defining ideal I, and I write down the coordinate ring, call it Rx. And that's a canonical symplectic pairing between V and its dual. And I have two ring of polynomial differential operator, which I call dv and dv check. So dv is the ring of polynomial differential operator V, and the corresponding, and likewise for V check. Okay, so this will be the main ingredient I'm going to use to cook up a class of differential system. So here's sort of a baby example to keep in mind. PGL3 acting on P2, and the line bundle I choose is O3. So of course this setup will correspond to elliptic, the cubic curve in CP2. That will eventually be the connection to geometry. Okay. So again, the notation I had earlier now specialized to this. So V becomes this 10-dimensional representation on the space of all degree 3 homogeneous polynomial. And CV is just this polynomial function ring in 10 variable. A check here form a dual basis of the A. And again, Z is this 10-dimensional representation of SL2. PGL3. And the embedding is exactly this cubic embedding. So the ideal is, again, classical. It's defined by these Veronese binomials. You take product of 4 pairs of these, 2 pairs of this guy in an appropriate way, so that the power come up to be the same, and that will give you one quadratic equation. And you can describe the coordinate ring of P2 inside of P9. It can be embedded back inside of this polynomial ring of 3 variables. So namely, is generated by all the cubics. Okay, so your symplectic pairing is just the standard one, and this ring of differential operators now become just about algebra in 10 variables. Okay, 10 variables A0 to A9 and the dual variable. Okay, the two are playing complementary roles, but you need both of them in the picture. Okay, so now comes the definition of a tautological system. So now you look at something called the Fourier transform, something that everybody is familiar with. So this is literally the sort of the classical Fourier transform on linear space. And so what do you do? This gives you a set up an isomorphism, a ring isomorphism between these two rings, which does the following thing. It takes this variable a check to the corresponding first order constant derivation. Okay? And it takes the derivation in the a check variable to a multiplication operator but with a sign. Okay? So in the abstract setting, I was told that this transform was introduced by Riemann in one of his books. But in this setting where the space on which I consider my D module are just affine space, this is the Riemann's definition now specializes to this, which so happens to be the classical one. All right, so what is the upshot of this? Well, under this transform, any polynomial function on V now get traded in for a constant polynomial differential operator. Okay. All right, so here's my definition. Pick a complex number. So I start with the 3 initial data. Now I have a 4 piece. So given this four pieces of initial data, I want to define a left ideal of dB check generated by this class of operators. So the Euler operator is a familiar one, but this time I allow an arbitrary homogeneous degree given by this complex number of data. Okay. And the symmetry operator are given by coming from the group, acting on B. And finally, the polynomial operator are given by the Fourier transform of the defining ideal of my tautological embedding. Okay. So I get a left ideal or equivalently a differential system. I call both of these a tautological system. Okay. So there are many important cases where this is this class of
Sorry.
yes.
So it's in dB check. So you have PA. The first part, the polynomial operator.
Yeah.
So one of them is PA check, and the other one is P.
Right.
A, no check.
Right. Because if you take a polynomial function, which is P of AB check, and you do a Fourier transform to it, it becomes a polynomial differential operator by substitution. For every a check variable, you replace it by a del A variable. Okay.
So do you include higher order operators or
Yes.
just binomial ones?
No, there will be lots of higher order one in this generality, depending on your.
I see. I find
Right.
it's not just the Veronese.
No, not anymore. I mean, you gave me a G variety and an equivariant line bundle, you get this. Yeah. In fact, for you see that even for toric variety, these operators will no longer be quadratic. Most of them will be high order. Okay. So as I just alluded to, this class of system is actually well studied in many important cases. So this is sort of a general setup to include all of them. Okay, so let me be specific. Oh, okay, before I get to the history, let me make a few remarks about sort of basic properties of this system. So first of all, you notice that in my definition of the tautological system, which by the way, throughout this talk, I'll refer to a generic tautological system by this letter tau. okay? Without carrying all the data with it. So it turns out if you just look at the definition formally, it makes perfect sense if you forget the geometric setup, the line bundle and so on. Just replace this embedding ideal with any O ideal in this polynomial ring. And beta, you can replace it by a Lie algebra character of this trivial central extension of G. Okay? So instead of a single complex number, you can replace it by a full character. And the whole definition will make perfect sense. Now it turns out that this is not just a sort of a mindless exercise. This generalization turns out to be necessary to deal with the Fano and general type case. I don't think I have time to get into the specific of this, but I thought I'd mention it as a remark. Okay, so here are a couple of basic properties about tautological system. So if one assumes that X has finite number of G orbit, then tau turns out to be a regular polynomial. And so that means any formal power series solution is automatically analytic, and the sheaf of analytic solutions has finite rank. It's a local system. Of finite rank. Oops. So this basic result is proved in two earlier paper with Song and Yao and Yao and myself. Okay, so the second basic property is that there's actually a bound on the solution, on the generic rank of the D module, under the condition that if the embedding coordinate ring Rx is Cohen-Macaulay. Okay, as I said, the tau is actually well studied in many important cases. So here are two of them. So if you specialize X to a toric variety and take G to be the dense torus, then tau would reduce to a GKZ system. And the basic result I mentioned earlier are very well known in this case as well. If you specialize X to a certain spherical variety, typo here, should be singular, spherical variety of a semi-simple group, then this reduces to what we call a Caprano system. So Caprano studied these things in 97 as a natural generalization of GKZ. Okay, so what about the case of you take a projective homogeneous space, G mod P. So G is semi-simple and P is parabolic. So it turns out in this case, you can give it a very explicit description of the polynomial operator that literally goes back to Coston. I mean, Coston didn't study the differential system, but what he studied was the embedding ideal. He wrote down an explicit set of generators for the defining equation of the embedding. And it's given by this very nice formula. So you take the quadratic Casimir of G. Okay. So this is a you can think of it as a linear operator on the second symmetric power. So that means it acts on this second order differential operator. So CG is a linear operator on this vector space generated by these quadrants. Okay. And it turns out that there's a particular eigenvalue of, well, CG acts diagonalizably. Okay. And there's a particular eigenvalue of this quadratic Casimir that you have to project out. So you take this projector, CG minus lambda, and hit on this symmetric power representation. The statement is that this projected space gives you all the generator for the polynomial part of my tautological system. Okay. And as a numerical example, if you specialize to CPN and the canonical bundle, anti-canonical bundle, these constant operators are exactly the very easy. Okay. All right. So I've set up now three things. I have a period sheaf, I have a residue sheaf in the geometric setup, and then I have this general setup in algebra I call tau. What is the relation between the three gadgets? All right. So let's assume that X is a final G-variety. And I want to consider the universal family of Calabi hypersurfaces in X. I will talk a little bit about the cases where these are either general type or final hypersurfaces in a moment. But let me now stick with Calabi. All right, so here's a statement generalizing the CPN case that the period sheaf and the residue sheaf of my family are both subsheaf of the solution sheaf of tau. So what you found is sort of just like the case in 1995. You found a differential system, sort of the obvious operator you can write down that kills your period sheaf and residue sheaf. And that's given by tau. All right, so before I get more into the tautological system, let me mention make a couple of remarks about general type and final. So you could redo the whole setup by replacing the anti-canonical with a very ample line bundle L, under the condition that this twisted line bundle is big and with section. So in this case, the generic hypersurface would be a general type, parameterized by this section space. So it turns out that you can get the analog of this theorem for this setup, but you do need to make a few substitutions. So instead of V check being the parameter space, you need to replace it by this larger space. It's given by the product of two section, dual of two section space. Okay? The original section space that parameterized the hypersurfaces and this twisted line bundle. And the ideal now, the defining ideal for the embedding now have to be replaced. It's replaced by a certain G invariant non-radical ideal in this larger function ring. Okay? So the key point here is it's no longer a radical ideal. So this ideal could have a generator given by things like del square or del x del y, which are as polynomial equation, these are sort of non-reduced. Okay. And likewise, you can do it for final hypersurfaces. In this case, you have to do the sort of the opposite replacement. So L, you can take a very ample line bundle L under the condition that this, this twisting is ample and with section. And then you can consider the corresponding final hypersurfaces parameterized by section of L. In this case, you get a similar tautological system where the parameter space has to be replaced by this space, where the twisting now depends on which L you take. So P actually depends on L in some way. Okay? I don't want to get into some the specific, but there will be some positive integer L that you need to put in here in order to make the correct parameter space. Anyway, so the upshot here is that in all three cases, Calabi, general type, and final, you can set up this differential system for the periods and residues. Okay, so here's an example of the final case. So the P4, this is a well-known, well-studied classical case. P4, O3, and in this case, P turns out to be 2, and tau that you wrote down turns out to govern the periods of the so-called cubic threefold given by this Poincare residue. Okay, so all right, so where are we? We have now a tautological system. We know it's connected to the original geometrical problem, the periods and residues, and so the goal then is to give some develop some understanding of period and sheaf via this route. by giving a good description of tau and then study it. Okay, so to make the rest of this discussion as least technical as possible, I'm going to specialize to the case Cardial and forget genotype and final. And I'm going to specialize to the case where the character is 1, namely the geometric situation. Okay. All right, and I will make a further assumption that my projected variety, G variety, has finite orbit. Okay, so I want to introduce the following notations. So again, previously we have introduced V, that's given by this guy, and this trivial central extension of G, well, which I call G hat. I want to write down the universal section. So this is given by this quadratic polynomial in the A and A check variable. You can think of it as the section, well, the polynomial function that parameterizes all sections simultaneously. In the sense that you think of it as a function such that if you evaluate it at each point, if you evaluate at one point in the parameter space V check, B, you get a section. You recover a section of N, okay? And every section occurs this way. So this is, and hence the name universal section. Okay, next, this object also plays an important role. This is called a character D module. So you obtain it as follows. You take the D module on the variety X, tensor it with this one-dimensional representation of G, and this whole thing can be thought of as a right G hat module, and then you tensor it with this trivial one-dimensional G hat module. What you get is a left D module on X. I will denote that by dx beta. This D module appears prominently in geometric language everywhere. I mean, this is a very commonly used construction. Okay, next, I want to look at this so-called universal complement. So what is it? So this is simply the set of all pairs in this product where the universal section is non-zero, has non-zero value. Okay. So it is called this way because at each base point, the fiber of this bundle is actually isomorphic to the complement, and hence, so U is a space that parameterizes all such complements over the parameter space G. Oops. Okay. Now I want to introduce a couple of maps. The first is the projection map from this universal complement to the parameter space V check. I call this map pi check. So this is an affine morphism between two spaces, and so you can it induces a functor from the bounded derived category of polynomial D module on U to the one on V check. And I call it derived push forward pi lower plus check. And so this is just given by the usual Gauss-Mani connection. It's given by this derived push forward. Okay. So here's the first result about a sort of a homological description of tau. The statement is that there's a canonical isomorphism of D module between tau and this D module defined by this derived push forward. So this is the degree 0 homological piece of this D module in the derived category. So this is given by the fiber product of structure sheaf on V and this important character sheaf. As an immediate consequence, so a few lines of calculation, you show that the solution sheaf of tau, namely this gadget, hom of tau into this, at any given point, So that this is a germ of solutions at B. It's given canonically as a sheaf cohomology, compactly supported sheaf cohomology. Over the complement, what is this coefficient? Well, the coefficient is the derived solution sheaf of the character sheaf. So this is the sort of the dual version of the Riemann-Hilbert correspondence. So what this says is that you can now express all solutions of tau, all local solutions of tau, sort of neatly as compact supported cohomology classes. Okay. So this will have a lot of interesting consequences, as I will discuss next. So for example, again, a simple calculation. You see that this character sheaf project onto the structure sheaf. And so you plug that in, and this isomorphism now yields a surjection from tau into this D module. And this D module, according to this calculation, is an isomorphism whenever G generates Tx. So namely, and whenever you have a projective homogeneous G variety, you get a very simple description of tau in terms of this structure sheaf. Now I want to take the home of this description, and I'll get the following injection. So dualize it. I get a canonical injection from this middle degree homology of the complement into the solution sheaf. And you can write down this injection in a fairly straightforward way. And that's this. Sort of the expected one. It's exactly given by integration. Okay. All right, so this is the sort of the key link between sort of, in the language of D module, between the residue sheaf and the solution sheaf of tau. Because this map is injective, as I indicated earlier, you automatically get a bound on the residue sheaf. So it's bounded below by this complement cohomology and above by this solution sheaf. These results are generally very difficult to get, by calculation alone. So you have to appeal to some D module technology. Okay, and you specialize this bound to the case when G generates Tx, namely the homogeneous case. Then you get a formula for the dimension of the solution sheaf, given by the middle primitive cohomology plus this this like an alternating sum. So this is a simple calculation using the Giesen sequence. Okay, again, let's specialize the homogeneous space. Because of this equality, and you see that this second inequality becomes an equality. And so you get two things for free. One is that the residue sheaf is now exactly the solution sheaf, which means that you solve half the Riemann-Hilbert problem for this case. So you have nailed down a differential system for the residue sheaf. For the period sheaf, unfortunately, there's one criterion that you have to further satisfy. Namely, the primitive cohomology has to be 0. So it gives you a very short criterion for when tau solves the Riemann-Hilbert problem. As an example, if you specialize to the projective space case, or that dimension of x is odd, you get back the earlier result of Bloch, Huang, and so on. Okay? So this solves this is the old completeness problem that I mentioned earlier. Okay, the second application is since I'm almost out of time, so let me just mention one more application. All right, so this is So this is sort of the opposite case to the homogeneous case. So instead of a single orbit, now you demand that your space has fixed point. Okay? So as a test example, let's consider the case of toric variety. If you consider the case of toric variety, you take G to be your dense toric T. And as I mentioned earlier, tau now reduces to a GKC system. Again, as I mentioned, the GKC system is never complete. So this is an injection, but it's never surjective. Okay, so here's a theorem, a recent theorem. So it tells you to what extent this map failed to be injected. Okay? It tells you that, in fact, the remaining stuff that is left out by the complement cohomology are given by the following group. Okay? Namely, this map actually factors through this relative cohomology. What is this relative cohomology? Well, it's the relative cohomology of this pair given by the complement, and D here is the union of toric divisor inside the toric variety D. So this is the D that appears prominently in mirror symmetry as the large complex structure limit. Okay, and there's a good reason for that. So you look at this relative pair and the relative middle homology. You show that this integral map is exactly extend the injective map to an isomorphism. We call this the chain integral map. So what it says is that all the solutions are given by integral over chain rather than cycle, where the chain are required to be bounded by this canonical toric divisor D. Okay. So this result was actually motivated by an earlier paper of physicists trying to interpret the extra solutions of the GKC system. In the case of mirror quintic. So in the case of mirror quintic, if you write down the GKC system, everybody knows that there are 5 solutions rather than 4. Which the first 4 give you counting of rational curve, but the 5 is kind of stick out like a sore thumb. So this physicists try to make sense of it physically by interpreting them as some kind of integral of chain bounded by D brane. I should also point out that this statement is also parallel to the one that was studied by physicists in the type 2 open string theory, particularly Walker and his co-worker, where they study chain integral where the chain are bounded by a holomorphic curve in Calabi-Yau threefold. So this is sort of an analog of that for GKC system. Okay, since I'm out of time, I'll stop here. Thank you.
Questions?
So, I have a question about this last theorem.
Yeah.
So the way you're setting it up, it looks like dynamics of self-intersection of anti-canonical hypersurfaces inside some ambient space, because you're computing these relative periods which tell you how but these are really B-branes, right? I mean, you intersect one hypersurface with another, you get the B-brane. So it seems to be like a double geometric situation where in one hand you have a funnel with a Calabi-Yau hypersurface in it, on the other hand you have a variety of general type sitting inside that Calabi-Yau hypersurface, which is the intersection with the other sequence. So is there any way to actually do a mirror of the whole situation? So it's really about pairs of Calabi-Yau hypersurfaces inside the given funnel and mirroring the base locus of that together with everything else.
So you want to do mirror symmetry for the whole pair?
Yeah. Well, it's a triple really, right?
Yeah. haven't thought much about
But do
that.
you see any behavior in these periods that you're describing, which looks like a hypergeometric function, rather than, you're saying it's a solution
Yes.
to a GKZ system, but is there any classical hypergeometric function coming out? Or?
It is. I mean, this chain integral, if you expand it near the large complex structure limit, say if you take YD to be very close to the toric divisor D, you can write down explicit formula for this, and it's given by exactly this sort of renormalized GKZ hypergeometric function. And if you take that formula, so this formula was written down in around 95. Take this formula. This formula takes value in the mirror the mirror ring, so to speak, or the mirror toric ring, and so you can set out a isomorphism between these functions and the quantum sort of the deformation of the quantum cohomology ring, meaning this period this chain integral actually parameterizing quantum cohomology product on the mirror ambient toric variety. So you can set up the isomorphism in a very, very concrete way. So in that sense, it's sort of it deals with sort of mirror symmetry of the Calabi hypersurfaces a la Batiev and Borisov, and at the same time deal with mirror symmetry of the ambient toric variety, the final ambient toric variety, at the same time. Yeah.
Other questions? So let's thank both again. We'll resume at 10:15. Yeah, 10:15.